Welcome friends. So we are discussing module 7, that is transient response of electrical network. In the previous session we have discussed the fundamental properties of inductor and capacitance under transient condition and steady state condition. What is transient condition? Whenever we are making some switching operation, it immediately creates some disturbance to any network that we refer to be a transient state. On the other hand, if we performing something on some network and if that network is operated for a longer duration of time, so effectively that network does not experience any disturbance from the outside. So we say, or we refer that network has reached at its steady state. So mathematically transient means t is equal to 0, and mathematically steady state means t is equal to infinity. Infinity does not necessarily mean that it is a large time. So if you consider t is equal to 1 second or 2 seconds, it is infinity in context of this network performance. Okay. Now we shall continue our discussion on this topic. We will see the behavior of the different network topologies. That means we shall see three different networks: series RL, then series RC, then series RLC. What will be their behavior under transient state? So let us discuss. Now, prerequisite, there is some prerequisite before discussing those networks. So we have some differential equations. You should know their form and their solution. Proof is not required here. So first, if you refer to equation 3a, that is the differential equation, it is dy dt plus ay is equal to b. That is a well-known differential equation. What is a and what is b? A is constant and b is either a constant or a function of time. So if you come across this type of differential equation, you can straight away write its solution as yt, that is equal to b by a plus k into b by a k into e to the power minus at. That is the solution. What is k? K is the constant of integration. Okay, so this is the form and this is the solution, you should remember. Moving on to the next form, differential equation form. So if you come across this form, dy dt plus ay is equal to 0, dy dt plus ay is equal to 0. What is a? A is a constant. Soon you will find this type of differential equation, then its solution is yt is equal to k into e to the power minus at. K into e to the power minus at. So if you come across this type of differential equation anywhere, you can directly write the solution as yt is equal to k into minus a in t. Lastly, if we have this type of differential equation, if you come across a d2i dt2 plus b dy dt plus cy is equal to 0, where a, b, c all are constants, right? Then you can write the differential equation. The solution is yt is equal to k1 alpha t plus k2, sorry, it's not alpha, it's ct and k2 dt. Again I am repeating, yt, its solution is k1 yt, that solution becomes yt, it's k1 e to the power ct plus k2 e to the power dt. What is k1 and k2? K1 and k2 are the constant of integration, and c and d are roots of the differential equation, right? This is the differential equation, second order differential equation. So c and d becomes the root, and the solution is from this well known formula, minus b by 2a plus minus root under b square by 4ac by 2a. So if you come across this form, you can write directly solution by this equation. Soon you will see these forms. Now let us first discuss our first topology, that is transient response of series RL network or RL circuit. So you have a R, you have a L is connected to a DC battery V. Now if you consider the switch, it is initially open. Okay, the straight line represents, so this line, this arrow represents the initial condition, and this curved arrow represents the transforming condition. Okay, from it is, that means initially it was open, now it is making from off to on, open to close. Okay, so as a result, as it is open initially before switching, since before switching it is open, then the current flowing through the inductor, okay, current flowing through the inductor is 0. So that is why I am writing I0 minus is equal to 0. So immediately after switching, just after switching, it becomes I0 plus is equal to 0, because current flowing through the inductor does not change instantaneously. So this is written here, equation 6. Now you can write the KVL equation. It is well known KVL equation, V that is equal to RIT into L di dt. V is equal to RIT plus L di dt. So if you take the derivative, if you take L, that means you divide the entire equation by L, you will get di dt. Okay, then R by L into IT, then that is equal to Vt. So di dt plus R by L IT is equal to V by L. So it is in the form of dy dt. So this equation 7, this differential equation 7, you find this form in di dt plus ai is equal to b, that is differential equation 3a of this type you will find. So immediately you can write its solution. What is the solution? IT, its solution is IT, that will be is equal to B by A, right? B by A plus K into e to the power minus AT, right? E to the power minus AT. So now you can write the solution. So let us explore that. So IT is equal to, now what is B? B is equal to V by L. B is equal to V by L. And what is A? A is equal to R by L. So we have written V by L by R by L plus K e to the power minus, now what is AT? A is equal to minus R by L into T. So IT, as a result, the expression becomes V by R, LL cancels, into K into e to the power minus T by tau. Okay, so what is this new term tau? New parameter tau. Tau is nothing but L by R. It's called time constant. It's called time constant. So L by R, it's called time constant. So let us understand the significance of tau very shortly. So for the time being, just consider tau is equal to L by R of a series RL circuit. Now this is actually, it should be plus, okay, V by R plus IT is equal to V by R plus K. So you need to evaluate the value of K, that is constant of integration. You should evaluate the K. So in order to find out the value of K, you must impose the initial condition. So what is that initial condition? This is the initial condition. What is that? At t is equal to 0, IL is equal to 0. So that is we going to write at t is equal to 0, I becomes 0. So IL and I are all same because it is series circuit. So whatever I, that is also is equal to IL. So we put IT is equal to 0, that is equal to V by R plus e to the power K into e to the power K into e to the power minus 0 by tau. Okay. So if you evaluate or if you solve this equation, you will get K is equal to minus V by R. K is equal to minus V by R. So overall IT, overall expression for IT becomes V by R into 1 minus e to the power minus t by tau. So this is the overall expression of IT, that is the current flowing through the inductor. Now let us first try to plot what is IT, what will be the nature of IT, right? Let us try to first plot. Let us use x-axis, time in x-axis, time, and in y-axis let us consider IT. So from this expression you can clearly understand that when t is equal to 0, when t is equal to 0, I0 that will be is equal to 0. Why? Because this is V by R, it is 1 minus, actually this is because V by R, V by R that multiplied with 1 minus e to the power minus 0 by tau. So e to the power 0, so this term will be 1, so 1 minus 1 will be 0, so I0 will be 0. Okay, so at this point, at t is equal to 0, we have current value is 0. Quite obviously, because initially there was no current. Before switching, current flowing through the inductor was 0. So just after the switching, it should be also 0. Now if you put t is equal to infinity at this equation, t is equal to infinity, that means in a long time, large time, t is equal to infinity. So this equation becomes V by R 1 minus e to the power minus infinity by tau. So this e to the power minus infinity, it will be 0. This term will be 0. So I infinity, that will be only V by R. So at some large time, so let us say this is t is equal to infinity, at some large time the value will be V by R, right? So this will be V by R. So we get initial point, we get final point. Now we need another intermediate point to have the nature or to understand the nature of this curve. So let us now put I is equal to tau, t is equal to tau. Let us put t is equal to tau. So what happens to this equation? V by r into 1 minus, now e to the power minus tau by tau. So that is equal to V by r 1 minus e to the power minus 1. So if you solve this, you will get 0.632 V by r. 0.632 V by r. That means it is almost 63.2%. Let us say this is tau, t is equal to tau. And let us say this is almost 63.2%. So 0.632 V by r, right? So we got another point here. So if we join this curve, we shall get a similar this kind of nature. So which is shown in figure 4a, figure 4a, this type of nature, roughly. It's not a linear, right? Now if we extend this analysis, so now what will be the resistance? That means voltage drop across resistance. So it will be R into IT. So it will be just V by R into R. So it remains as it is, V into 1 minus e to the power minus t by tau. So again, so this will follow the same nature. It will follow the same nature, and this value is V. This value is V, right? And you know VLT, that is the voltage across the inductor, it is L di dt. So if you solve this L in, if you take the current time derivative of this current, so you will get this expression VLT is equal to V into e to the power minus t by tau. So you will get this type of expression. Why? So let us explain. VLT, that is equal to V into e to the power minus t by tau. At t is equal to 0, let us find out V0 or VL0, that will be equal to V into e to the power minus 0 by tau. So it will be actually V. This will be actually V. So at t is equal to 0, we are getting some voltage V. So this value is V, right? At second condition, at t is equal to infinity, we get VL infinity, that is equal to V into e to the power minus infinity by tau. So it will be 0. So at t is equal to infinity at larger time, this value will be 0. So we get initial point, we get final point. So to get the nature, we shall have third point, intermediate point. Let us check t is equal to tau. So VL at tau, it will be equal to V into e to the power minus 1, because tau cancels, so it will be actually 0.368 V. It will be 0.368 V. So it will be almost 36.8%. Okay, so this point, let us say this is tau. So it will be 0.368 V, 36.8%. So if you plot this curve, it will follow this locus. Okay, so we shall get these three expressions for current, voltage across resistance, voltage across inductance. Now let us try to understand what is the significance of time constant. Now as it is already done or is done, actually if you put T is equal to tau in the current expression, you will get current is 0.632 V by R. That means 63.2% of V by R. Again, if you put T is equal to tau in the VRT expression, it will give you same result, 63.2% of V. And for the last expression, if you put T is equal to tau, you will get VLT is equal to 0.368 V, so it will be 36.8% of V. Okay, now let us try to understand the significance. Okay, so if you consider this curve, you see it starts from 0 and it reaches to V by R. So it starts from 0 and it reaches to V by R at T is equal to infinity. So if you consider 0 is equal to 0% and V by R is equal to 100%, so total change in magnitude is 100%. So after T is equal to tau, what is observed here is that the magnitude becomes 63.2% of the total change. What is, I repeat my statement, at T is equal to tau, okay, at T is equal to tau, the magnitude of the current becomes 63.2% of its total change. Now what do I mean by this total change? Total change is this 100%. It starts from 0%, it ends at 100%. So total change is 100%. So it becomes 63.2% of the total change. Okay. So that is the significance of the time constant. Here also it starts from 100%. It starts with 100%. That means the expression of VLT. Right, it starts at 100% and it ends at 100%, so its change is 100%. Okay, now at time constant, at one time constant, the magnitude becomes 36.8% of the V. However, the change is 63%. 63 point change is this much, so that refers 63.2% change. The idea of the time constant is that it is the time in second. Of course it is second, it is the measure of the time after which voltage or current, both voltage or current, becomes 63.2% of its total change. It's very important. Its total change, if you measure 100%, then after one time constant you will observe that the magnitude becomes 63.2% of what? 63.2% of its total change. That is important. Okay, that is the significance of the time constant. And most importantly, for in this case, for a series RL circuit, you initially find that tau we have assumed. What is tau actually? What is tau? Tau is equal to L by R. Tau is equal to L by R. So for a series RL circuit, time constant equal to L by R second. Time constant is equal to L by R second. So it is actually the response of series RL circuit. We have got the expression of IT that is the current flowing through the circuit. We have also observed the voltage across the resistance, voltage across the inductance. There we have found that they are not in actually linear in nature, it is exponential in nature. And we have introduced a very important conception of tau, which is time constant, and the definition of tau is that it is the time in second, okay, it is the time in second after which magnitude of voltage or current, it will be true for both the parameters, voltage and current, it becomes 63.2% of its total change. That means you have to measure the change from 0 to 63.2%. So the change is this. Okay. So it is the change 63.2% of its total change. That is the definition of time constant, and for a series RL circuit, the time constant becomes L by R second. So with this, I am ending this part. We shall continue this discussion for two more topologies, that is for series RC circuit and series RLC circuit, from the next session. Thank you.